gradient is a vector of partial derivatives of a function. Each component of the gradient shows us how fast our function is changing. If you want to optimize a function, you just need to go to the negative gradient direction, because the gradient is the steepest ascent direction of a function at a given point. To build an intuition behind the gradient descent, we can create the simplest possible scenario: tangent line of a function at a given point. The tangent line of a curve is a straight line that touches the curve only once without crossing it. It shows us the instantaneous rate of change of a function at a tangent point, because the slope of the curve matches exactly with the slope of a tangent line. Let's consider the point slope form of a line. X1 and Y1 in this case is the point of a tangency. Okay, and we have Y minus Y1 equals M times X minus X1. And let's break this equation down, and the slope M we can define as race over the run, or changes in the vertical directions, or y minus y1, over the changes in the horizontal directions, x minus x1. Basically, we wanted to detect the instantaneous changes of the function at a given point. As far as I remember, our definition of derivative, it's exactly what we need in this case, yeah, because it matches with this idea of instantaneous rate of change. So, meaning that we can replace this basic term to the function and the derivative of the function. We can rewrite it like this: y minus f of x equals f prime of x times x minus x1. So we know how to program the derivative. We can use the central difference for any function, and we can make an interactive plot for, let's say, x squared, yeah, to play with this tangent line, and we'll see how it works. And you can see that our y value right now completely dependent on the right hand side. We use f at the point x0 plus derivative at the point x0 and x minus x0. So we can program this without any problems in Python, yeah? I want to mention that the central difference, or symmetric difference quotient, is employed as the method of approximating the derivative for a bunch of calculators, yeah? TI-82, TI-83, yeah? And they use this method with h equals 0.001. So if we use the central difference, it's not so bad. Now let's define a tangent line function. We receive approximately the same bunch of arguments, but as the last one, instead of h, we have a x0. So for the implementation, let's look at this formula and make exactly the same in Python. First of all, we need to get f of x 0. We need to call f of x 0. It's quite easy. So then we need to compute the derivative, yeah? df of x 0. We need to call the central difference, yeah? And we provide f, x, and let's use h with this default value, 10 to the negative 3 power, as for the Texas Instrument calculator. And we need to return our f of x0 plus df of x0 times x minus x0. So I hope that this is what we need. Yeah. Okay, and now let's build an interactive plot. This interactive plot, it's just a little tricky, but for a little. We call this interactive plot with the interact, yeah, and this interactive plot just binds f and x arguments to this high-order function that returns this function underscore interactive plot that lives in the closure of the function interactive plot, meaning that we just we bind these parameters on the higher order level function, and then we have this function that makes a job for us, yeah. And this interact, it provides x0 as the variable, yeah, as the argument to the underscore interactive plot. The most important information in this example condensed in the slope of our function. So, and I add this text slope to the label of our tangent line and to the legend of our plot. Let's run this code. If the slope of a function at a given point equals 0, or if the derivative of our function equals 0, it means that it's some sort of an extremum point. And to understand what type of extremum we have at a given point, we need to analyze the sign of the slope before the extremum and after. Before this extremum point, we have strictly negative sign. And the slope at a point -3 equals -6. But if you go towards the extremum at the point 0, 0, you can see that our tangent line is less and less steep. And the slope value from the absolute perspective is less and less every step towards the 0. Then it's completely horizontal. We have no any change of the function at a given point. After this, it's obviously that we have the positive sign, and it's more and more every step, the value of our slope. And the tangent line is more and more steep, yeah? And at the point 3, the slope equals 6. If we change our sign from negative to the positive, it means that we have a minimum point. We can flip our parabola. Let's flip it. We need to add just a negative sign to this function. Let's run this code. Okay, we need to change the y limit. Let's set up from -10 to 1. Okay, and let's make the same analysis. Now you can see that we changed the sign of our slope from the positive to the negative. It means that before this extremum point, our function is increasing, then we have this inflection point, and the function is decreasing. It means that we reach the maxima point of our function. Now let's add one more, yeah? Let's use numpy sine of x. Let's run this code. We need to change the limits, yeah? Let's use from -1.2 to the positive 1.2 for y limits, and for the x, let's leave -4 and 4. So great. And let's analyze these two extremum points. And first of all, let's check this one, yeah, right extremum. Let's go to the positive direction, and you can see that the sign before this extremum point is positive. Then we have this extremum, yeah, somewhere near the 1.57. Yeah, we have 0 exactly at the point 1.57, but it's like 1.577777. And then the trend is changed. Yeah, we have the negative sign. So it means that we change the slope of our function from the positive to the negative. It's some sort of the maxima. And for the left extremum, you can see we have the slope negative before this point, then it's less and less steep, and it's positive after. Yeah, so from the negative to the positive, it means that we reach the bottom of our ball. What if we start from some random point on this function, let's say -2, and then just follow the direction of the derivative? Yeah, in this case the derivative is strictly positive and equals 4. Yeah? Let's say we go to the direction just based on the sign. We have a positive direction, and let's say that we make one step in the positive direction. Yeah, let's say to the -1, and we still have this positive value for the derivative. Yeah, and it equals 2. Let's make one more step in the positive direction. Let's say 0.5. Yeah, and you can see that we are closer and closer to this maxima point. Yeah, let's check for the positive side. If we follow the direction of our derivative, let's say -4, and it means that we need to go to the left side, let's say to the point 1, you can see that direction towards the maxima, yeah, to the negative side. Let's say we use 0.5, make one more step to the maxima, and this slope value with the sign, it's like a compass. It shows us the direction of the steepest ascent of a function, yeah? And if we will follow the slope direction, we can find the maxima of our function. So I believe that we can program this behavior. Let's make an algorithm that just based on the slope, make a one step in the direction of the steepest ascent of our function. Let's build an ascent function. And we have a bunch of arguments, f, x0 as the starting point, and steps. It means that how much steps will we make, yeah, in the direction of the steepest ascent. And we know that we can compute d f of x0 as the central difference for the function f, and we provide the x0 as the input of our function f. So we won't touch the h value. Let's use by default h equals 0.001. And now we need to update the coordinates, yeah? And x1, it equals x0 plus the df of x0. So just make one step in the direction of the derivative. Okay, cool. And we need to do this 5 times. Yeah, we need to do 5 steps. And let's create the result list. and we need to initialize the loop. Let's build a range, the steps, yeah, how much steps do we need to make? Great. And we have this x1, we need to add it to the result. Let's append x1 to the result of our ascend function. And we basically need to return the result. Every time when we make a step, we need to change the x0, yeah, because our x0 equals x1, yeah? We just use the previous value and calculate the next one. So it means that we need to include to the result this x0 as the default value. Okay, great. And now let's build a plot. Okay, and we use the negative x squared as our function. So then we plot the ascent. We have x0 and steps as the arguments of the plot ascent. Right over here we generate the input and the output of our function, just to make a plot with the original function. As the next step, we build the XPath for the ascent, yeah? Let's call this X ascent XPath. And then we build the ascent YPath. We convert this XPath list to the NumPy and square the result, yeah, just to build the bunch of Y values. XPath against the YPath, and we add a bunch of errors, yeah, because we have this ascent path, and every step we just move in the direction of the steepest ascent, yeah. And for this purpose we have this tricky plot loop. So let's run this code and you can see the result, yeah. Something definitely wrong here, yeah, because we have this horizontal line, yeah. So it looks like our ascent path just bouncing around. It looks like this step of the steepest ascent is too big. Let's add one more parameter and we call it like learning rate. And by default, let's install 0.3, for example. We will apply this learning rate for the derivative value. Let's multiply this derivative by the learning rate. By this way, we just reduce this step size, yeah? I just don't want to reproduce this behavior when we just bouncing around. We want to make something different, yeah? We want to make one step, yeah, in the direction of the maximum. And for this purpose, we need to reduce the length of our step. We need to add this new parameter learning rate to the interact and initialize it as the float slider. And right over here, we need to use the learning rate too. And I want to provide this learning rate directly to the ascent, yeah? Just if we want to make some experiments and change this learning rate. Let's run this code. Okay, and right now let's use 4 steps, 5, 6, 7, 8, 9, 10. And you can see that we're pretty close to the maximum point of our function, yeah? We make this bunch of steps in the direction of the maxima, yeah? And I suppose that it's almost perfect match, yeah? Okay, and we have two hyperparameters. We have steps and we have the learning rate. Let's increase the learning rate. And for the higher learning rate, the faster we reach this maximum point. And for the 0.4, just 3 steps and we in the maximum point. For 0.5, just 2 steps, yeah, and we reach the maximum point. And let's install something like, and it's very interesting, yeah. It's just too much, yeah. In this case, this learning rate is just too high, yeah. We starting to bouncing around, yeah. Let's change the max for this learning rate to 1, and let's use the learning rate equals 1. And this picture, it matches exactly with our first version of the algorithm, yeah. But if we reduce the learning rate, and you can see that if the learning rate is less than 1, our algorithm, yeah, and our basic path just starting to go towards the maximum point, yeah. And less learning rate just change the behavior of the algorithm, yeah. And we need to find some healthy balance between the learning rate, between the step size, yeah, and between the number of the steps, yeah. And I suppose that for this exact case we need to use like 5 steps. For the learning rate, let's say 0.3, yeah. It's kind of almost perfectly detect this maxima point for the function. And if we follow the exactly opposite direction, yeah, negative derivative, it means that we will go to the steepest descent. If we change a sign right over here, yeah, from positive to the negative, we go to the steepest descent, yeah. And I can show you how it works. It's exactly the same function except this sign, yeah. In the ascent, we add to the initial coordinate the value of our slope times the learning rate, yeah. In the case of the descent, we subtract the same value from the initial coordinate. Okay, then I change the plot path, yeah. I have the same logic. I have a high order function, yeah, plot path with this f and path builder, and I have this like a function in the closure, yeah, underscore path. It lives in the closure of the plot path. And instead of the ascent or descent, I call the path builder right over here. And then I can choose any function to build the standard like function visualization. So great. And let's run this code. And you can see the result, yeah? For the negative x squared, yeah, it's kind of obviously that we goes straight to the infinity, yeah? And probably never find anything. Okay, let's change this negative x squared to the x squared. And now it's much better, yeah? It goes exactly to the minima, yeah? And if we let's change the learning rate. Let's use, for example, 0.3. You can see that we just pretty close to the 0. Let's just increase this a bit, yeah? And now it's exactly 0. Again, you can play with the number of steps and with the learning rate, yeah? You can change number of steps, or you can change the learning rate. And you can see how it works, yeah, how it performs. So basically, it's kind of gradient descent algorithm that can find a minima for the function, yeah. And this descent function, it's basically just gradient descent, but instead of the gradient, we use the derivative, yeah, and the direction of our derivative. But this quite simple scenario, it's everything that we have for the gradient descent. Yeah, we just follow the direction of the derivative. Yeah, in case of the gradient descent, we follow the negative direction of the derivative. And basically, it's everything that you need to know about the gradient descent. Yeah, just follow the negative direction of the derivative.